Hey class, this is going to be your 15.2 lecture. 15.2 starts about line integrals. There's two different kinds of line integrals. Technically, when we evaluate them, we're doing it all according to this first way, a scalar line integral. But we are going to also talk about line integrals of vector fields. So we'll start with a vector and we'll end with a scalar. We're still going to end with a scalar quantity for all of these integrals. So just to remind you guys, Calc 1, integrals look something like this. We might find the area of that shaded region, right, where we have left and right bounds of a and b. We have a hat or a height function of f of x. Pretty standard stuff. And really, scalar valued line integrals aren't that different. So here in 15.2, what we've got is instead of having a flat, straight x-axis to run off of, the base of our integral is some curve, and we can take it to be a curve in the xy plane. We could actually take it to be a curve in space. This is just easier to draw. And then we have a height function along that curve, f of x and y. So for each point x and y on this curve, there's a given height, and then we integrate that height over that curve. And one of the applications for this surface integral is it would give us the area of this roller coaster looking structure. So you can think of that as like an old-fashioned like Screaming Eagle style roller coaster that curves along the ground but also goes up and down along its path. And so then here we could find the area of the cross supports that hold up the track. This part over here, I just got a little ambitious and started to write out the formula. We'll get that on the next page, and it's kind of small there anyway. So that's the main difference between a line integral, a scalar line integral, and a Calc 1 integral, is just that this base is already kind of curvy. And we're going to have, you see C is going to be a vector curve, just like we had back in chapter 12. And in fact, all we're going to do really is just stretch this out and pretend it is along a t-axis. So the s in our integral refers to arc length, and we can compute this integral by straightening c into a pretend t-axis. So we'd integrate along this curve c. As t goes from a and b, our original curve goes from r of a to r of b, and so we can instead think of t as going from a to b. Just a reminder from chapter 12, the derivative of arc length with respect to time is your speed, the magnitude of r prime. And so if I just kind of multiply my differential over, not technically, but that's what it looks like, we get ds equals the magnitude of r prime of t dt. So here's the formula written out. This is the same formula that was boxed on the previous page. We can do our line integral with respect to arc length instead by taking the line integral of f, plugging in our function. Remember, every x and y in here was actually a point on the curve, so we can use r of t to represent each x, y, and then times the magnitude of r prime dt. And this here is just going to be a Calc 1 integral once you simplify it, once you have actually plugged in here and here. So how about an example of this? So we're going to evaluate the line integral over c of x minus y plus 2z. So this is my little f, where c is the circle, and here's our vector equation for the circle. We have a circle that sits on the x-axis, always one away from the yz plane. 3 cosine t, 3 sine t, where t goes between 0 and 2 pi. Pretty standard chapter 12 kind of curve. The only thing a little bit different is that we did offset it from one of the coordinate planes, but really it's just a circle. So the different pieces we're going to need. Remember, this was f of x, y, and z. So just calling out that this is x, this is y, and that's z. And we're also going to need r prime. That's a quick derivative, and that's a really easy magnitude because of trig, right? So now the integral over c of f of x and y ds is equal to the integral from a to b of f with r of t plugged in times the magnitude of r prime of t dt. So here's my f of x, y, and I guess z in this case. I don't need the z over here, that's fine. And so t is going to go from 0 to 2 pi. That's the limits for t. That's my a and b. F with x and y and z plugged in is going to be 1 minus 3 cosine t plus 6 sine t. The magnitude of r prime is just 3 dt. And then a little quick calc 1 integration later, and we get 2 pi. Another example with a little bit of a different curve. So we're going to integrate over c, 2x minus 3y, where c is the line segment that goes from negative 1, 0 up to 1, 0, and then down from there to, from negative 1, 0 to 0, 1, and then from 0, 1 down to 1, 0. This one is easiest if we parameterize it into two pieces. So if we parameterize this first line segment, we'll get r1 of t is negative 1 plus t, comma t, as t goes from 0 to 1. That's just the parameterization of a line segment from way back yonder. C2, same way, r2 is going to be t, 1 minus t, as t goes from 0 to 1. It's okay that our limits for t here are the same because I'm actually going to split this line integral into two separate line integrals. I'm going to do the line integral of f from here to here, and then the line integral of f from there to there. And that's perfectly fine to do. And this is, in fact, what you do anytime you have a corner. Remember that typically we want our curve C to be smooth, but if it's only piecewise smooth, we just split it at the corner and write it as multiple integrals. The same way in Calc 1 we would handle it if we had just a single removable discontinuity or a jump discontinuity in a function, something like that. So I'm going to do the integral over C1 and C2. So C1 was parameterized. This was C1, and C2 was parameterized by R2. And so I take the derivative of each of them, pretty straightforward. Take the magnitude of each of them, it turns out to be the same. That's not a big surprise. Both line segments were the same and we weren't moving in any funny way. And so then first I'll compute the line integral over C1. So for x, I'm going to, for the integral over C1, for x, I'll plug in negative 1 plus t, or t minus 1. So that was my x. And for y, I'll plug in t. And then I need to multiply it by my magnitude of r1 prime. So that is this piece right here. And that's a quick Calc 1 integral. I'm going to say that a lot. We do a little bit of work to get down to basic Calc 1 integrals. That's what we're doing with these line integrals. They're a little different animal than a Calc 1 integral, but we're gonna do them here in 15.2. We're gonna do all of these by evaluating a Calc 1 integral before it's all said and done. So then the same thing, I've got to do the line integral over C2. In this case, on C2, my x is t, and my y is 1 minus t. My magnitude of r2 prime was the same, so I still get the square root of 2. And again, Calc 1 integral later, negative root 2 over 2. And then just a reminder from the bottom of the previous page that the line integral that we were looking for over C is equal to the line integral over C1 plus the line integral over C2. So I can just add up those two values. I get -6 root 2 over 2 or -3 root 2. Let's see. Ooh, hang on a second. I'm pausing the recording. Lost a page. All right, sorry about that. I had left a page out of my stack when I got started. So this is our next page. So the other kind of line integrals is line integrals of a vector field over a curve. So we need a vector field. F is a vector field. We want it to be continuous. And we want it to be continuous on a region that contains a curve that is either smooth or piecewise smooth. Your book talks smooth at first and then they switch it later. It really, just like I showed you in that last example, piecewise smooth is good enough. We can always split it up into different integrals. And at first anyway, we're going to want the curve to be parameterized by arc length. Most curves are not parameterized by arc length, and so we are going to have a method just like we had before of dealing with that. So then the line integral of our vector field f over c, this is the integral over c of f dot t ds, where t is the unit tangent vector at each point on the curve. So this line integral, and I'm going to say this later, this is the same line integral we'll use for work. It's the same line integral we'll use for something called circulation. And essentially, it is a measurement of how much your vector field and your curve are working together, working parallel to one another, right? When the dot product gets larger and larger, the closer these two vectors are to parallel. So we'll compound this. Remember, an integral is basically an infinite sum with a limit thrown in for good measure. And so we're summing up a bunch of these dot products. And so these quantities are going to be larger the more places on your curve that your curve and your vector field are moving together. Where they move directly orthogonal, this will actually add nothing, right? Because the dot product of two orthogonal vectors is 0. So that's what we're doing with the line integral of a vector field. And our vector fields here, that like we might consider them to be a force field if we want to think about, or a gravitational field if we want to think about something like work done. But there's lots of different ways we can look at this. So big question, what if C isn't parameterized by arc length? Well, it's not really a big deal, because even though we say there's two different kinds of line integrals, technically, and this is the nice thing about the way our book likes to write this as f dot t integrated over c ds, is f dot t is a scalar, which means that whatever that dot product is, we're going to be back as a scalar line integral. And so if c is parameterized by r, then we can actually do, just without knowing what that is, that's going to be our little f when we're done, we can actually do this integral by multiplying it by the magnitude of r prime of t dt, and now it doesn't depend on s at all. So if c is parameterized by some time or some other parameter that isn't arc length, we can account for it by replacing ds with magnitude r prime times dt. But it gets better than that, because t was our unit tangent vector, and so from back in chapter 12, we know that's r prime over the magnitude of r prime. So our magnitudes of r prime, which is honestly really the annoying thing about scalar line integrals, is that sometimes we've got an annoying square root in there from taking that magnitude. I avoided that in my examples, but you won't get to avoid it in every homework problem. So sometimes you're going to have a little bit of work to do on your Calc 1 integral. And so we can actually evaluate this line integral as the integral from a to b of f dotted with r prime of t dt. No parenthesis, that's extra. That's a nice upshot. This is a nice formula right here. And it's the one, you can't quite see it. It just says this is how we're going to do most of our line integrals of vector fields in 15.2. We're going to get some other methods to do line integrals of vector fields in 15.3 and 15.4. 15.3, we're going to talk about, well, what happens if our vector field is particularly nice. And in 15.4, we're going to talk about, well, what happens if our curve is special in some way. And in those cases, we'll get some other ways to not parameterize, but to solve these line integrals. So this is a little question of notation. I don't usually like to disagree with the books that I'm using, and this is not a strong disagreement. Your book prefers this notation, and this notation has the side benefit that I just mentioned, that it emphasizes that since that's just a scalar, this is really not a different kind of integral. We just have a different formula because, well, stuff works out nicely when we are doing this particular type of line integral. But I really like this notation, the integral over C of f dot dr. These are the same, and I'm going to show you they're the same. I think this is more memorable and help in terms of helping you get to the formula. And I recognize that, you know, if you're doing take-home tests right now, you're probably not as worried about memorizing formulas. But, you know, I think it's just useful. It's also shorter, like just as things go, and it's a little cleaner to me. It just kind of talks about, well, how much of f is moving in the same direction as my curve without stopping to think, well, that really I'm talking about, it has the same kind of, you know, the tangent vector to my curve. I don't have to stop and think about that. There's none of this ds. It's very, very simple. So real quick, dr dt equals r prime of t. And so all I have to do is replace dr with r prime of t dt in this formula. And then since I'm integrating with respect to t instead of r now, I switch from a to b, my limits from a to b. And so that's the same Calc 1 integral that we said that our line integral of a vector field was. And so they are equivalent. And it is, you will not hurt my feelings at all if you prefer this notation. And they honestly both have their benefits. But when I write one, I tend to think of it this way. I tend to only think of this when I want to kind of come up with the formula, when I want to think about what this means specifically about the tangent vector, that sort of thing. So let's see, let's do an example. So to pay respect to both notations, that's how I'm writing them today, evaluate the line integral of f dot t ds over c, which is the same as the line integral of f dot dr over c, where f is the very simple vector field xy. You might recall in the 15.1 lecture, I told you that it was really common for us to use that sort of a radial field, and I'm going to use it right now, on the parabola. So my curve is the parabola with the vector form 4t t squared, where t goes between 0 and 1. So the first thing we need to do is plug in our r of t to our f to get our f in terms of t. Now in this case, because f is just x comma y, which is the same as what r is, we get just 4t t squared. I hesitated to lead off with this because most of the mistakes I've seen grading the chapter 15 exam in the past that have to do with these line integrals is people assuming this is always the case, that I always just replace f of t with r of t, and that's not it at all. F was x comma y, x is 4t, so 4t goes there. Y was t squared, so t squared goes there. In the very next example, it will be different, although that one is weird in a different way. In the pursuit of nice numbers, we often result in a little bit of weirdness. The other thing I'm going to need is r prime of t. So quick derivative formula says the integral over c of f dot dr is the integral as t goes from a to b of f with r of t plugged in dotted with r prime of t. Now, I didn't emphasize that on the last page, and I only emphasize it here because that's how I wrote it up there. But yes, we do want this in terms of t. We want this to be a Calc 1 integral where t is our only variable left. So you have to plug in r of t and get everything in terms of t. So we've already found those. So that's just 4t, t squared dotted with 4, 2t, still integrated as t goes from 0 to 1. Do the dot product, do a quick Calc 1 integral. Another example. So we've got the same, we're doing a line integral of a vector field. On the semicircle this time, r of t is 4 cosine t, 4 sine t, t between 0 and pi, and here our vector field is negative yx. So the first thing I'm going to do is plug r of t in to f. So I get f in terms of t by plugging in. There's x, it goes there. There's y, it goes there. So we get negative 4 sine t, 4 cosine t. I mentioned there's just a trifle of weirdness here, and here it is. When I take r prime, I get the exact same vector. So in the last one, I had f equals to r. On this one, I have f equals to r prime. I guarantee you there are cases where f is not equal to r or r prime. It's just I need more involved f and maybe even a more involved r, and it would not be hard to come up with one. So formula again, we're going to do it by switching so that our integrals in terms of t. Plugging in, there's my f of r of t, there's my r prime of t. I need to take a dot product, and trig tells me that one is easy. I believe it is 16, and so that's an easy Calc 1 integral. We get 16 pi. So those are the two types of integrals, except that there is a little other notational consideration. So we also call this integral of f dot dr or f dot t ds the circulation of f on c. And that's what I was talking about, a piling up of f and c moving in the same direction. And that's the idea of circulation. And we also can call it the work done in moving an object along the curve c through a force field F. We'll talk more about that in 15.3 when we talk about conservative vector fields. And yes, having alternate ways of referring to these things does mean application problems. Specifically, you'll have a couple of work problems. There is another sort of line integral of a vector field, and it's called a flux integral, or just finding the flux. So the flux of f across c is the integral over c of f dot n ds. But n is just one particular vector that's orthogonal to r prime. See, we just take the components of r prime and we flip them, and then we put a minus sign here. So n dotted with r prime will be 0, n and r prime are orthogonal, but they have the same magnitude. Well, actually, n is a unit vector, sorry, but the top part here has the same magnitude as r prime. And so in our formula, if we were to do that with the ds, the magnitude of r primes would still cancel. And so this is just like our f dot dr integral up above, except instead of dot r prime, we have this orthogonal to r prime vector. We don't emphasize flux line integrals. Flux is a measure of, like, so here, if that's my curve C, and let's give a really easy field F. So like right here, my field and my curve are directly orthogonal to one another. So there, the flux would be quite high. Here it would be a little less because my n, right, is going to be that way. So the dot product wouldn't give you its full effect. And if this curve were to come back here some which way, then someplace here where they would be parallel, the curve and the force field, there would be 0. So it's a lot like circulation, except we're looking at how much the curve and the field are orthogonal. And a way you might consider this is like if you had a stream and you were trying to pull, you know, a boat or something across the stream along a path, you might get some sort of a flux idea for a line integral, as opposed to, you know, if you were trying to float the boat more or less down the river, then, you know, the circulation would tell you about how the river was pushing the boat along, at least in that direction. Flux plays a bigger role with surface integrals starting in 15.6. So you'll see a flux integral here or there in your homework. You will not see a flux line integral on exam 4, except possibly, let me put it this way, you won't see a line integral on 15.4 that you have to consider as a flux integral. That is my caveat. There is a little bit in 15.4 where you can look at them either way. And real quick, why is that? Well, if we don't know what our force field is, then if I just know I have some dot product here, and then numerically, this is equal to a circulation integral for a different force field along the same curve. Let me say it that way. So if I take a particular field, if I have F and I take the flux on F over C, and I have a different force field G, there is a force field G, so that this integral over C is the exact same as this integral over C. And so every flux line integral could be thought of as a circulation integral over a different vector field, and not even that different of a vector field. If F equals little f G, and I have my vector y prime negative x prime, then this dot product here is going to be g x prime, right, except negative plus f y prime, but that would be equal to the vector field negative g f dotted with x prime y prime, where these guys come from the same curve C. So this would be my vector field cap G. That was my vector field cap F. So for an orthogonal field that is otherwise has the same magnitude as F at each point, then I can compute a flux integral as a circulation integral. And I'm not asking you to do that. That's really a side notion, but that's why we don't always emphasize that. Some books don't even talk about flux line integrals, and our book does. And in 15.4, we're going to get a formula for circulation integrals and a formula for flux integrals, and we'll talk about them, but I'm not going to emphasize them. When we get to surface integrals, you can't avoid flux. But at that point, we downplay circulation a little, because circulation means more for these line integrals, and flux means more for surface integrals. So that's it for 15.2, guys. Have a good one.